Alright, so now I want to talk a little bit about the transformed area approach for reinforced concrete sections. So it's important that we start our discussion here with the major caveat that the transformed area approach is really only valid in the linear elastic range. And this is the linear elastic range for the combined cross section, so for both the concrete and the steel. All right, so what is the transformed area? The transformed area is basically what area we would need to have for the cross section if the cross section was to be made out of only one material. So we can put a definition to this. This is the equivalent area of the cross section if it was made, or if it was only made of one material. Now, when we approach this in reinforced concrete sections, what we do is we transform the steel into an equivalent area of concrete. So we're going to take our total reinforced concrete section, or we call this the gross area. This is A sub G. And what we're going to do is we're going to transform the steel. So first we have to take the steel out of the reinforced concrete section, and we're left with just the area of the concrete. And then we're going to transform the area of the steel. So we're going to take these kind of empty holes where we took the steel out, and we're going to transform that into an equivalent area of concrete that matches the stiffness of the steel. Now, steel is much stiffer than concrete, so we are going to end up with a larger area of concrete than the area of steel we initially had. So we're going to represent this kind of larger area by what we call N times A sub S. And N is going to be the modular ratio, and we're going to talk a little bit more about that here in a couple minutes. All right, now we have this increased area of steel. That's the equivalent area of concrete that matches the steel. What I want to do is I want to take one of those A sub S's and plug it back into the missing holes in the concrete section so we can end up with the gross area as shaded there in blue. And then that's going to leave us additional concrete material, and we're going to put them kind of in little wings off to the side. And now this is going to be N minus 1 times A sub S for just the area along the edges. And we do this in this fashion just to kind of put them at the same depth within the concrete cross-section, so that later we also will do some calculations with moment of inertia. So it's important that we kind of keep these areas, these little wings, at the same location as the rebar. All right, if we recall back from mechanics and materials, I have taught you that basically we can solve any engineering problem using these three items: equilibrium, kinematics, and material law. All right, equilibrium, we relate the forces. So in our particular application with this force on the concrete column, we'll say that the total force equals the force in the concrete plus the force in the steel. When we move on to kinematics, in kinematics we relate displacements, or equivalently we could relate strains. And here for our column, the total deflection of the column will be equal to the total deflection of the concrete and the total deflection of the steel. And we'll call this equation 2. And then finally, from our material law, as long as we're in the linear elastic range, we can use Hooke's law that says that the deflection is equal to PL over AE. But in general, as long as we're in the linear elastic range, we can also say that the strains in the concrete are equal to the stresses in the concrete divided by the modulus of elasticity of the concrete. and the strain in the steel is equal to the stress in the steel divided by the modulus of elasticity for the steel. I'm going to call those equations 3 and 4 respectively. All right, so using those equations, we're going to formally determine the modular ratio. So if I take equations 3 and I take equation 4 and I plug it back into equation 2, we will end up with the following result. We'll say that the strain in the concrete and the strain in the steel have to be the same, and therefore the stress in the concrete divided by the modulus of elasticity for the concrete equals the stress in the steel divided by the modulus of elasticity for the steel. Now we're going to solve for this in terms of the stress in the steel. So I want to solve for the stress in the steel. So this is now the modulus of elasticity of the steel over the modulus of elasticity for concrete times the stress in the concrete. Now, this ratio of the modulus of elasticity of steel to concrete is what we refer to as the modular ratio, that what I just put in parentheses. And that modular ratio is what we defined as N. So we can say the stress in the steel is N times the stress in the concrete. So again, our modular ratio here, N equals E sub S divided by E sub C. All right, continuing along, we can now take this latest equation, which I just labeled here as equation 5, and we can plug that back into equation 1. And we'll get that the total force in the section is equal to the force in the concrete plus the force in the steel. That was equation 1. So this equals the area of the concrete times the stress in the concrete plus the area of the steel plus the stress in the steel. And now substituting the piece from part 5, equation 5 there, we get that we have the area of the concrete times the stress in the concrete plus the area of the steel times now N, the modular ratio, times F sub C. All right, regrouping this, we can group the areas together. So now I have the area of the concrete plus N times the area of the steel, all times the stress in the concrete, and this would give me the total force in the concrete section. And then if you recall back to the very beginning when we talked about the transformed area, we said that we often use the gross area instead of the column, so the length times the width of the column. So if we do that, now we have to have the gross area, and then we have to take one A sub S away. So we take N minus 1 times A sub S. And we'll take all of this multiplied by F sub C. So this area in the brackets, this is what we refer to as our transformed area for the reinforced concrete section. And again, I just want to stress the point of with that diagram on the first page. And so we'll just kind of look at it again here. This is the gross area, so the entire length times width for this, whether it's a beam or a column, it's the total area. And so that equals the area of just the concrete. Plus, now we're transforming the steel into an equivalent area of concrete, and that's equal to N times A sub S. So now it's all concrete. We're going to plug some back into those holes. So we have to take 1 away from the transformed area of the steel. So we get AG plus, and again, we take N minus 1 times A sub S. So N minus 1 times A sub S is represented by the shaded red pieces,